Lessons with, what do I got? Label number 3. So what happens there? Negatively charged species can act as bases, and they can act as nucleophiles. If it acts as a nucleophile, where do we go? We would go to our hemiacetal. What do we know about our hemiacetals? They're unstable, so they revert very quickly back to just our standard carbonyls. So the ethoxide acting as a nucleophile is not a good answer here. Right? If we were being asked a hemiacetal question, then we might go down that path. How would you know you were being asked a hemiacetal question?
Answers.
You'd look at your multiple choice answers, and your multiple choice answers would show hemiacetals. Right? That would be a big tip-off that that's why you're supposed to be answering hemiacetals. But in general, acetals are usually a bad answer because they aren't particularly stable. When are acetals stable? So when are acetals good answers? Those of you moving into biochemistry, this is the reason why acetals are important and talked about in OChem. They're good answers when they are cyclic. When does cyclic acetal show up? Carbohydrates. Okay. So if you have to move into biochemistry, good luck. It isn't that bad, sorry. That was kind of mean. It isn't that bad, but there's an entire section on carbohydrates where they talk about the chemistry of cyclizing acetals, okay, or forming hemiacetals and acetals. Carbohydrates naturally cyclize because they can form these stable 6-membered rings. Okay? So when we're looking at acetals, pretty much the only time they become important is when they're cyclic, and that's really carbohydrates, that's really biochem. Okay? Which means, since we are not cyclic, we are not looking at hemiacetals, we're looking at our ethoxide acting as a base. So where's there an acidic hydrogen? It is not the aldehyde hydrogen. If we tried to go through and show the aldehyde hydrogen being removed, we would have a negative charge on that carbon. Okay. Carbon can't stabilize a negative. Students oftentimes try to say, well, don't I have resonance? Well, draw it, see what happens. What happens if I attempt to do that? I would have a triple bond to oxygen. Am I allowed a triple bond to oxygen? Yes. Okay. We will actually see active species forming the triple bond to oxygen. That is actually not the problem with this structure. I didn't do anything to the lone pairs on the oxygen, which means they are still present. I've exceeded the octet. That's why this structure fails. Okay. So that is a bad resonance. I can't stabilize the negative charge, which then means not an acidic hydrogen. Whoops. So where do I find an acidic hydrogen? Either go red or we could go blue. Which one? Red because? Okay, one option is it's closer to the electronegative element. That does make it acidic or more acidic. That does not make it acidic though. What makes it acidic? That there's resonance. When I remove those electrons, I would form a negative charge on that carbon, just like I had before, and that in and of itself is bad, except I can draw resonance. That puts the negative charge on the oxygen. Oxygen can stabilize that negative charge a little bit better. That's what's driving this reaction. Between those two resonance structures, which one is the active form? Which one has the active nucleophile? The left structure has the active nucleophile, the active negative. Why is the oxygen not active? What is the difference between oxygen and carbon? Oxygen is more electronegative. By being more electronegative, what is it doing to those electrons? It is holding them, thereby it cannot react them. Those electrons can come back down. We can show these electrons now come out and attack something. What would they need to attack? Something electrophilic, something positively charged. This is where most students tend to trip up. Okay? It can attack itself, sort of. If I draw a second molecule, I can have those electrons attack the carbonyl carbon and break the structure open. The result being negative 1, 2, 3 carbons. Yeah. And then our oxygen. Is that structure stable? No. What can it do? We can take a hydrogen from somewhere in the environment. That also tends to trip people up. Almost always you'll see a solvent written underneath there. What's that solvent? Ethanol. Why would we pick ethanol? That's how we get ethoxide, is by using ethanol. Okay? So the ethanol provides that acidic hydrogen. We can go ahead and put our hydrogen on. What structure do we now have? We have an aldehyde and an alcohol. We have the aldol. Okay. What is special about this structure? It still has a hydrogen at the alpha position. Is that alpha hydrogen more or less acidic than our first hydrogen? It is more acidic. It still has the resonance stabilization that we had in the first case, but now we have an inductive withdrawing effect of our oxygen, of our alcohol, making that purple hydrogen even more acidic, which means I can deprotonate it with the negative charge. I could go through and show resonance, and I keep wanting to draw resonance. Okay, showing the electrons going up towards the carbonyl to prove that stability. Okay, because we've already shown that, instead I'm going to show the electrons come back down and kick out OH. This last step is known as the condensation. Why is it a condensation?
You're losing water.
If we look at the overall loss in this case, we lost that purple hydrogen and we lost OH minus. Put them together and what do we have? Water. Why is it called a condensation? When we ran the reaction, just put it in a container and let it run, we noticed that there started to be a condensation dripping on the condenser or dripping in the reaction. Why was there condensation? Water was formed. Okay? Condensation is a fancy term for the elimination of a small molecule from your structure. It does not have to be water. Okay, but historically it was water, that's why we see the term condensation. It is really just an elimination reaction. And we would end with our final product. Kind of makes sense? Okay. Questions?
Does it matter that you technically lose 3 hydrogens?
Did we technically lose 3 hydrogens?
Those 2 hydrogens there, right?
So we lost the 2 hydrogens off our alpha position. And then what did we lose?
Well, and then we lost the OH as well.
What OH? That OH?
Correct.
Did I start with OH?
No. Yes. Oh, so you gained a hydrogen anyways.
If you look at the net change to this reaction, you lose 2 hydrogens and 1 oxygen, and that is it. There's no other loss of hydrogens. Okay? To get the OH as a leaving group, we had to put a hydrogen onto the structure. Okay? That hydrogen was not already there. Okay? So our environment or our solvent mediates the transfer of hydrogens back and forth through this reaction. Okay? The big net change is ultimately just the loss of that oxygen and 2 hydrogens. Nothing else changed. That's a lot of mechanism stuff to draw out. I wonder if there was a shortcut. If we go back and look at our starting materials and say, I think this is going to go through an aldol, how would I know it could go through an aldol? Okay, I need to see acidic hydrogens, and in particular, what type of acidic hydrogens? For instance, if I drew this as a starting material, does this have an acidic hydrogen? Yeah, would that do an aldol? No. Okay, so it's not just that I have an acidic hydrogen, it's that I have... Nope. Getting closer, we have alpha hydrogens, and those alpha position is in direct reference to that carbonyl. Okay? And in particular, an aldehyde or a ketone, at least at this stage. Okay? So I have to have those for my acidic hydrogens. The next part, I'm going to have to react it with a strong base. Okay? So if those conditions are met, I can look at my answer choices and be like, acetals aren't on the menu, so that means I'm going with my aldol mechanism. Okay? So what I would go through and do is draw out the structures. So there's the first one, and then here's the second. Okay? So I've drawn my two equivalents stacked underneath each other. Okay? In the very first step, I'm going to make the red one a nucleophile by removing a hydrogen. So that carbon becomes nucleophilic. What does it attack? The carbon of the carbonyl directly underneath it. So there's my new bond. There would be the OH. If I suspect that this is a condensation, okay, how do I know that I should be looking for a condensation? Okay. Do I have two acidic hydrogens at the alpha position? If yes, that's a really good sign that I'm looking at a condensation. Okay. There's another thing that we have to be kind of pesky about. Read the directions carefully. If the directions, there aren't directions here, okay? You have to read your directions a little bit more carefully. If they say we want the aldol product, should you do the condensation? No, why not?
It would ask you.
Yeah, it specifically says I want just the aldol. Should I do the condensation? What does the condensation do? It takes off the alcohol, which means I don't have an aldol anymore. Right? So if we're asking specifically for the aldol, that's what we have to stick with. Can I help you?
Excuse me, I'm sorry. I had to call it, somebody left a flask. Did you see it in there?
A flask?
Yeah. That's what it said.
Not that I've seen.
Okay, sir. Thank you. Sorry again.
No worries.
We saw you bring it in.
Was it any good? So if we shift back, condensation, we have that alpha hydrogen. So we should go ahead and do the final elimination. And there it is. Question? So we're removing hydrogens from our red carbon, and they are constantly forming bonds to our blue, though it looks kind of purpley structure underneath. Okay. Eliminating that oxygen. And that now is our aldol condensation.
Yeah. You showed a quick how you do it with the ring, like the number one.
Number one's going to be a little bit different. Why is number one going to be a little different?
You only have one hydrogen.
I only have one hydrogen. Can I do a condensation?
No.
No. Okay. So that first one won't do the condensation. This is going to look ugly. Ishmael at least asked me to do it earlier, last time, and it's not going to get any prettier. Though I probably could have drawn it nicer than that. So we go through, we form the first bond. I still have the OH because there's no other alpha hydrogen. What happens?
Shouldn't attack the carbon. Oh wait. Okay. I just got it up there. All right.
Yeah, for those of you being like, that looks really weird, that's hard for me to
You
see.
had the OH
That's
there.
exactly why it's testing you on it.
Wait, what did you have before that? Didn't you have an OH right there?
The same exact thing.
Where? No, both of those were identical structures. All I did was kind of moved that up so that we could get at the nucleophilic carbon.
Yeah.
How would we know that there's no hydrogen available without drawing the structure?
Interesting question. How would you know that there are no hydrogens available unless you drew the structure?
Is there a short?
So the first response I heard was a phenomenal response. You draw the structure. That's how you know. You don't go, well, I think it's maybe that. No, you draw the structure. Draw it. That's the answer. Okay. Now, if you want to come up with your own shortcut and try and evaluate and say, well, I see this many bonds, so I know there's one implied hydrogen or two implied hydrogens, that's on you, and I'm going to tell you right now that's a horrible idea. Draw the structure. Okay. If you do it right, there's nothing I can say. Okay. But your best option is to draw it out. Okay, so if we looked at that top structure, if I look at the alpha position, okay, how many bonds are shown? 3, which means the fourth bond, I have 1 implied hydrogen. If we look at the structure underneath, which I'll now double circle in purple, and I look at the alpha position, how many bonds are shown? 2, which means 2 implied hydrogens. Okay? I would argue you should draw them. You should make sure you see it. Which is why every time we do this, what do? I draw the structures. I put those in.
How do you draw it so fast and so quick?
10 years of practice. 15 years of practice.
Really?
Yeah. Unfortunately, that's really the only way to get to it is just tons and tons and tons of practice. Okay? So let's make it more challenging. Take a look at the next one. You guys want to try it on your own first?
Yeah.
Good, I agree. Tell me what you get for a product. So, in most people's work that seem to be getting it, we've got our nucleophile shown on top. So there's our electrophile. So what happens is we remove those hydrogens. Those hydrogens come down, attack, and we'd form our aldol condensation, right? Is that what everybody got? I'm going to say absolutely that is not true, because unequivocally nobody wrote that.
You forgot one thing.
What did I forget?
The phenol.
Oh yeah, that methyl group.
No, not that one. The other one.
What do you mean? 1, 2, 3.
No.
1, 2, 3.
The other one. The other structure.
That one doesn't react, right?
What was that?
It doesn't react.
What do you mean it doesn't react?
I thought we told us earlier. It's still electrophilic. Why is that?
How many nucleophiles are in this structure? There is 1. How many electrophiles are there?
There's 2.
Which means
2 possible products.
there are 2 possible products that can come out of this.
So some of us got half right.
So some of you got it half right. Nobody drew this one out because you immediately went under the instinct, well, that one must be the electrophile. If that one's the nucleophile, I got to react them. Is that true? No. Okay. So you have to be very careful when you look at the aldols to evaluate nucleophiles and electrophiles. Okay. Remember, the biggest thing that happens in second semester is we stop having one nucleophile, one electrophile. We can have a whole smattering of them. Okay, so you have to be very careful when you go through to evaluate your answers to make sure that you don't make simple mistakes like that. Okay? Which means if we look at this one, we will also produce, which is what I believe most people were trying to draw, and the phenyl, because I don't want to draw benzene. Yeah? Good? Where does the alcohol go? So first it starts here. We still have alpha hydrogens. Those alpha hydrogens are removed, forming that extra pi bond and the elimination of the OH. Make sense? So are we good?
So, just to clarify, because we have 2 areas of
Yes.
So it could be an aldol crossed reaction or the same.
If we start going back to the textbook reference, right, we start with aldol reactions. Then you hear reference to crossed aldols. What are crossed aldols referencing? Everything that we looked at before, it was the same aldehyde reacting with itself. Does it have to react with itself? Or the same type? No, it can react with a different species. That's where you're getting crossed aldols. Right? So all that word is saying is you're bringing in another structure. That's it. Kind of, sort of? So how about the next one? But you won't make the same mistake again, right? Why has this one become so much more of a pain?
Because we have 4 different ones now.
Why do we have 4 different products?
You have 2 nucleophiles and 2 electrophiles.
I have 2 nucleophiles and I have 2 electrophiles. I get all the possible combinations of those, which means 4 possible products, which I think I drew correctly. 1, 2, 3. I think I got them. Okay? So when we talk about our reactions, I keep referencing negatives and positives. The reason why we keep referencing these negatives and positives is that when you look at your reaction, you should very quickly go through and evaluate your species and say, oh, that could be a nucleophile. Oh, that could also be a nucleophile. Well, and that can be, and that can also be an electrophile. And you should be quickly evaluating and coming up with a, oh crap, this is going to have 50 different products. That's a lot of effort for me to have to think through. Right? Or there's only 1 positive, 1 negative. I can get to an answer very quickly because all I got to do is put those 2 pieces together. By identifying those sites of reactivity fast, you don't have to go through a mechanism for each of those pieces. It's now just a question of connecting them. Kind of, sort of? Right? Again, that takes practice. I'm not saying this is just an instant you got it and you move on. Okay? So, things that we've seen so far. We have to have those alpha hydrogens to be able to react. We need 2 to do a condensation. Okay? If we have multiple nucleophiles and multiple electrophiles, things get messy very, very fast. Okay? Could I still potentially run a reaction where I limit some of those other reactions? Okay? Let's say the one I want would be this guy. Okay? To make that product, where was my nucleophile? Call it structure 1 or structure 2. Okay? So we're going back and identifying our reactivity. Okay? That new bond settles on that condensation section. Okay? The carbonyl was untouched, which means that's where my acidic hydrogens were, off of that structure, which means structure 2 was my nucleophile, which then by definition means 1 had better be the electrophile. How could I change this reaction to force that product? That's a much harder question, by the way. So if I just do 2 and the base, what happens? Okay. Yes, I form some nucleophile. There's my negative charge. That negative charge could now potentially attack electrophile because there's still electrophile present. So how can I form the nucleophile without any electrophile present, or at least minimize the presence of the electrophile?
Did you change that carbonyl in number 1 to an OH? Did you do something like that?
Changing number 1 doesn't fix the issue of the self-aldol with structure 2. Why is there an electrophile? Why is there an electrophile after that first step? That's a really hard question. What do you got? So this carbon right there is electrophilic. That blue circle, is that carbon electrophilic? So I don't accept your answer that there's a polar pi bond and that's why I have an electrophile. Because we're saying that circled carbon is not electrophilic. Why is it not electrophilic? Because this negative charge can donate in, stabilizing it, preventing it from acting as an electrophile. Everybody okay with that? Cool. So how do I make sure that when I do this first step, making the nucleophile, that I only make this species and there is none of this left? But I can't eliminate what I start with, sort of. We could try and limit it. It's still, unfortunately, not going to work very well. And here's going to be our big hint onto why it doesn't work very well. How can I make sure that I can force all that to go across? Okay, because remember, I want it all this way. How can I make sure it only goes one direction? The ethoxide? No, that's not going to favor that direction. That'll help produce more of it, but it's not going to entirely favor it. I want just that blue arrow. What is the difference between the blue arrow and the red arrow? One is reversible and one is irreversible. I think we used those words before. How about we use a stupidly strong base? If I used something like H- sodium hydride, what happens? The hydride comes in, removes the hydrogen. To reverse the reaction, what has to happen? That negative would have to attack hydroxide, or the ethanol, right? If we balance that out. What happens if I did sodium hydride? Where would my hydrogen now be? Where is that hydrogen now? H2, which is a gas. Can I reverse that reaction in blue? No. So what happens? Because I'm using a stupidly strong base, I quantitatively, meaning all of it, reacts to form the enolate, the active nucleophile. As we said, that nucleophile is no longer electrophilic because of resonance preventing that from being a nuclear or an electrophilic site. Which means now what happens? Now I only have a nucleophile, so what could I do? What do nucleophiles react with? Electrophiles. So what could I add now that I have a nucleophile? I could add structure 1. So if I break this into 2 steps, where I run the acid-base step first, and I run it as a stupidly strong base that is irreversible, I form only the nucleophile. Now I can follow that up with the electrophile. Okay?
Oh, that's what you have to do with the other thing.
And that's how I could get the majority of just that product. Am I still going to run into another issue? That stupidly strong nucleophile is also a base. The base could deprotonate instead of acting as a nucleophile, which would generate a second nucleophile, and we're going to start to get some other side products. So almost all of our aldols are not perfect yields because we always have this nucleophile base fight that's happening within them. So we can control it a little bit by stepwising our reactions and taking that into consideration to limit those other systems. Make sense? Hi. So if we take a look, the second to last one just went through with ethoxide first, which is what was initially suggested. That's a reversible reaction. We're going to get a fairly high concentration of the electrophile still present if we just use the ethoxide base, which means we still get multiple products. Only when we move to the quantitative, irreversible, stupidly strong base do we get a full conversion across, and now we can force only one product, or force mostly one product. Make sense? So when running our crossed aldols, we almost always have to run them in 2 steps. We don't have to run in 2 steps. Because if we went back and looked at this one, there really is only one nucleophile. And while we do have 2 electrophiles, we can expect a larger percentage of them to be the benzaldehyde structure, the benzaldehyde. Why would we expect a larger percentage of that one to be our electrophile?
Because if one's already acting as a nucleophile, you're decreasing that.
I've already decreased the population of this electrophile by making some of it a nucleophile. So odds are, sorry? And then the benzaldehyde doesn't have any hydrogens to create a secondary nucleophile. Okay? So when we run crossed aldols, we have to be a little bit more careful with our conditions to make sure that we don't run into those overlaps. Okay? So we need alpha hydrogens. Okay? There's lots of control issues that we have to watch out for. We should really only have one species having our alpha hydrogens. This is kind of a reagent control. Okay? Or we can make sure that only one species is allowed to enolize. Okay? This is using the base to control your reaction. Make sense? Okay. So, other things that we could worry about. If we went through and looked at this case, what base should we use? Or what's different about this new structure?
A lot of acidic sets.
There's 2 electrophiles. What else?
There's 4 locations that could be nucleophilic.
And we have 4 nucleophiles. What else is different about this structure in comparison to the ones we've been looking at? Yeah, there's symmetry. Maybe attacking itself is actually going to be a good idea. That's where this slide is actually headed. What is the big difference between this structure and the structures we've looked at?
There's multiple ketones.
Multiple ketones, that gets at multiple
no
sites. Multiple, actually what?
There's no aldehyde.
There's no aldehydes. Okay? We're using ketones. So in this case, we don't have an aldehyde. Would we do an aldol reaction? We might say no because we don't have an aldehyde. It still fits under the aldol type chemistry. Okay? So it still gets called aldol even though it's not an aldehyde. Okay? The next part comes in with, well, what's going to happen? Okay? As far as bases to use, all will pretty much do the same thing. If we're trying to force one reaction over another, we might stick with the stronger ones. Okay? Those really work for our crossed. In this case, the T-butoxide's probably okay. Okay? Why would I prefer the T-butoxide over the LDA and sodium hydride?
Maybe because it's not as specific, so we can
They're all going to be about the same specificity. Unfortunately not. Both LDA and sodium hydride. Sodium hydride is the bulkiest. Okay, that's the counterintuitive one because it's so unstable it never dissolves. So it's a multi-phase system. Has anybody used like a hammer and nail before? Yeah, so you've all seen you put a hammer up or a nail up to the wall and you can drive the nail into the wall, right? Has anybody used a sledgehammer to drive just a normal nail? Oh, a couple people. Okay. Has anybody used a wrecking ball to drive a hammer or drive a nail into a wall? No. Okay. Well, why not? And don't give me the wrecking balls are expensive, man. I couldn't afford it.
It's too much force.
It's too much force. You're using too much energy for the same thing that you want to try and accomplish. You could still. There are probably people, wrecking ball operators, that could probably very gently drive a nail into a wall. Okay. Why not use sodium hydride or LDA? We didn't call them wrecking balls. What did we call them? Stupidly strong. Okay? We want to use the strongest reagent that gets the job done without being excessively strong. Because if it's too strong, what could potentially happen?
Explosion.
Explosions. We could do a bunch of other stuff. T-butoxide will do exactly what it needs to. It needs to remove a hydrogen, and that's all I need to worry about. That's all I'm going to stick with. Okay? The other ones may work and may be more precise or precision-driven with what I was trying to do, but is that precision necessary? If it's not necessary, you should go the cheapest route. T-butoxide is significantly cheaper than the other ones because it's less toxic. Okay? So you'll typically see T-butoxide or oxides, some derivation of oxides used. All right, so now what happens in this case? So we've got a base and we've got heat. What is the heat a red flag for? Condensation. Okay? That's why we're seeing condensation, is water boiled and then it condensed so we could see it. So if you see heat written anywhere in a reaction, that should be an immediate red flag that you might be doing an elimination. It's not a guarantee, but you should immediately be thinking about doing the elimination. Yes?
Would this also, if you have heat, can you say that's a nucleophilic condition elimination as well? Kind of?
I do think it's interesting that you're bringing that up. It doesn't fit officially under the category of nucleophilic addition and elimination. We'll address why I think it might actually fit there when we look at this mechanism. Okay? So, multiple nucleophiles, multiple electrophiles. What should we try to do? So, okay, pick a nucleophile. Which one? 1, 2, 3, 4.
2.
Okay, 2. Is there anything just like 2? 3, which means what can I do? I can ignore 3. Why? It's the same thing. It's going to produce the exact same result, so I don't need to worry about it. By that same token,
1 and 4. Yeah.
I can get rid of 4 as well. Okay? I do have 4 nucleophiles. I don't have to evaluate each and every single one of them if I recognize symmetry in your structures. Okay? We still have 2 electrophiles. What should we do? Okay, I'm going to argue both of them are useful, so I don't quite understand which one's better.
They might both have to be used.
They will both get used for entirely separate reasons. What is our base going to do? Remove a hydrogen. Which one do you want to remove? 1 or 2? 2, okay. Sorry, Morgan. So we remove 2. Why are we allowed to remove the 2 hydrogen? There is resonance stabilization within that carbonyl. I am still using that electrophilic carbon, but I'm using it as a resonance stabilization. I'm not using it for a mechanism, okay, as an electrophile. Okay, which means, where's my electrophile? Over here. So I could go through and try and draw that result. Whoops. You might be like, God, that looks awful, Mike. I agree. I attempted to draw it in a way that I could close the loop, and I couldn't. We might say, well, what's our problem here? Okay. 1, 2, 3, 4. Well, that was pretty dumb. 4 things means a square. 1, 2, 3, 4. At position 1, what do I have? The ketone coming off, right? What do I have at position 4? I have the OH and that methyl. So we went through and counted 1, 2, 3, 4, 5, 6, 7 carbons. How many did I start with? 1, 2, 3, 4, 5, 6, 7 carbons. Numbering things seem to help find where those pieces were. It's a good idea. When dealing with cyclic structures or the formation of cyclic rings, you should probably number. Okay? Now what could happen? Or actually, let's pause. Do we like that structure? No, why not?
There's a lot going on.
I don't accept a lot going on. I will accept ring strain. Okay? To get a four-membered ring, you're really tightening down those edges. There's so much ring strain. The odds that that's going to happen, slim to none. What does that mean? Our second electrophile probably didn't attack. So what happens if it was our first? Isn't there also alpha hydrogens at position 1? Yes, they could go through an attack. Here's where I'm going to make a change, because one option is just drawing it all nasty and hook-legged like I drew that first one. The other option is going through and saying, what do I have? 1, 2, 3, 4, 5, 6, 7. What have I done with that arrow? Not a rearrangement, because I haven't moved an atom. Right? If anything, it's a coordination, and it's even then not really a coordination, because what did I do?
Just used a different.
I broke a pi bond. So this is an addition reaction. What attacks that pi bond? A negative, known as a nucleophile. So what have I done? A nucleophilic addition. It's an intramolecular nucleophilic addition because the insides are attacking. Okay? And instead of trying to draw that out, okay, in the weird goofy shape, I could say I've connected carbon 1 to carbon 6. I haven't broken any of the carbon bonds in between, which means what do I have? I have a 6-membered ring. 1, 2, 3, 4, 5, 6. At position 1, I just have a carbon. At position 2, what do I have? I have the ketone. At position 6, what do I have? I have the methyl, and I would have that O minus. That can get protonated. Now what happens? I still have an acidic hydrogen. And I would end with what type of reaction happened in that last step? This is an elimination. I formed a pi bond, so this matches the elimination. What did I eliminate from the structure?
The alcohol.
Hydroxide, so this is kind of like a nucleophilic elimination. Okay, so it kind of fits in that definition of nucleophilic addition elimination, but not quite, because that officially gets reserved for our carboxyl derivatives, which is our next unit. Okay? So we can do the aldols with ketones. We can also do them intramolecularly. Is this orange product a reasonable product to make?
Yeah.
Yes, because it's conjugated and 6-membered ring. Okay? The conjugation is a good point to bring up. That conjugation increases stability, which is what drives this mechanism forwards. Okay? That last step ends up being relatively irreversible. Okay? And we've got a final product that is now stabilized. Okay? Okay? We do have this issue of kinetic versus thermodynamic. It's kind of a minor point here. Why would it be a minor point? Only one of those enolates actually does anything. If we formed the internal enolate, what happens? The internal enolate put the nucleophile where? What was the issue with that one? 4-membered ring. I wouldn't be able to make a product. Okay, so I may not form a lot of the kinetic, but the kinetic is the only one that would work. It doesn't matter really which base I use. Okay, though preferentially we would prefer probably the sodium hydride or the LDA, okay, because then we don't have to worry about that secondary kinetic thermodynamic issue. Okay? Okay. So intramolecular allowed to happen as long as we get 5 or 6 membered rings. We don't get 5 or 6 membered rings, don't do them. I'm going to say that's a kid in the hallway. Yep. Conjugate addition reactions. So the next little layer that we throw back into this, the nucleophilicity ranking. Remember we had Gilman and Grignard? Gilman were not very nucleophilic, and in fact they only did 1,4 additions. They can't do 1,2. Grignard, go directly 1,2. Where are enolates? Right smack dab in the middle. The enolates will do equally both 1,2 and 1,4 additions. Why does that become problematic? You get 2 possible products coming out of them. Okay? So it makes it a bit of a mess. One of the things that we'll go through and do is tweak them a little bit. Okay? If we tweak them, in this case, what happened? Why is this different than a standard enolate? What would a standard enolate look like? I want that same carbon to become an enolate. Okay. These are now both enolates. What is the difference between those enolates? Okay, 1 oxygen versus 2 oxygens. What does that mean? More resonance. What does that mean? The right one is more stable. The more stable it becomes, the less likely it would react, meaning when I now mix it with this species, step 2, what am I going to get? 1,2 or 1,4? I prefer the 1,4. I don't have to worry about the 1,2. Whereas if I started with the initial enolate, this first one is now a mix. 1,2 and 1,4. Why is the next one only 1,4? What happens as we move from Grignard to Gilman? What happened to the strength of the nucleophile? Grignard to Gilman, the nucleophile became less nucleophilic. It is less nucleophilic because it is less negative. And that came back to our difference in electronegativity. When we look at the enolate shown here, okay, why is this one favor 1,4 and this one now 1,2 and 1,4? They're both enolates.
Can you show us how it's 1, 2, 1, 4?
1, 2, and 1, 4 is referencing what? Where it attacks over here. Okay, so when we're talking about our 1, 2 and our 1, 4, a nucleophile attack here is a 1, 4 addition. A nucleophile attack here is a 1, 2 addition, which is a very important thing to review before next Wednesday. Why does our boxed one get us 1, 4 and not a mix? For the same reason the Gilman does 1, 4, the same reason for our dione. It is a weaker nucleophile. The enolate sits perfectly in the middle between 1, 2 and 1, 4. The instant I do 2 resonance structures, I've now done what to the strength of the nucleophile? I've weakened it. With it now being weaker, what happens?
It's only able to react.
It can only react with the 1, 4. It can't react with the 1, 2.
How does more resonance in the nucleophile? Doesn't it strengthen it? That's what my initial thought was.
Okay, so let's go through and look at this, because it's been a while since we've evaluated this with everybody, so let's go ahead and try it. How does resonance weaken the nucleophile characteristic? Okay. Number 1, it is not a blanket statement. You can't make that as a blanket statement, so don't. Okay, I'm not saying you were. So we can draw a resonance, right? Everybody see that? Okay. We could also have done that. Everybody see that? Whoops. Okay. What happens with the other side? Helps if you draw the structure right, just for the reference. Is there another resonance? No. Let's look at the nucleophile. What atom was the nucleophile in both of these structures? Okay, our carbon. What is the charge in the carbon far left? What is the charge on the carbon in that resonance structure? -1. What is it in the next one? 0. So if I look at the average charge for that carbon, it is -1 plus 0 over how many structures? 2. The charge on the carbon is a -0.5. Since you're saying 0.5, we'll go with that. No, you're good. How about the next one? -0.5 was just easier for me to draw. -1, 0, 0. So if we look at the effective charge for that one, -1, 0, helps if we do a plus, 0 over how many structures? 3, which gets us? Of course you would switch to -1/3. Yeah. I bet you did that intentionally. -0.33. Which one's more stable? -0.33 or -0.5? -0.3 because it's less negative. Okay? More resonance led to more stability. It is not always the case. Okay? That's why you have to draw your resonance structures. Okay? Under most circumstances that you see, more resonance means more stability. But that is not always the case. Okay? And in fact, we will see counterexamples probably on Wednesday. Okay? So the big lesson that I want you to get out of this is that the conjugate addition comes back. 1,4 additions come back, and we can use enolates as nucleophiles. Okay? Because a single enolate gets us both 1,2 and 1,4 products, that doesn't work. Okay? We'd get too many products out of that in one reaction. That's like a crossed aldol. I don't want that. Okay? So we change the structure around, and we put a second resonance stabilization option on there. That stabilization weakens the strength of the nucleophile enough that it's now no longer a 1,2 addition. It'll only do 1,4. Kind of, sort of?
Are there any other carbon nucleophiles other than the green earth that'll only do 1,2s?
Yeah, the organolithium. Do I have the list? Here, sorry, let me scan through. Your textbook has a nice list between them, and I'm not sure I've got them in the slides. Yeah, I don't have them in the slides. Your textbook's at least not quickly available. Your textbook has them lined up pretty nicely, and I'll try and remember to find it in the interim, but there is a table that lists them out.
Like a cyanide ion work, or
Cyanide, I think, is 1,4.
1,4?
I think we'd... Cyanide, I know, does 1,2 for sure. I think given the option, it might do 1,4.
Okay.
So cyanide is a borderline 1,2, I think. Okay? This is kind of an interesting reaction because we would have expected a mixture of products. We didn't get a mixture of products. Why not? Because somebody adjusted the starting structure to make sure that we only get 1,4, not the 1,2. Okay? Because somebody has now created a nucleophile that only attacks one position and not the other, they get to attach their name to it. Okay? This is referencing our Michael reactions. When an enolate attacks a beta carbon, it's called a Michael reaction. Okay? So a Michael addition is just taking an enolate and reacting with the 4 position. So our Michael acceptors, okay? Alpha, beta, unsaturated, carbonyl. alpha beta unsaturated carbonyl. Alpha beta unsaturated carbonyl. Yeah, they're all just alpha beta unsaturated carbonyls. That one's not an alpha beta unsaturated carbonyl. Unsaturated polar pi bond. And carbonyls are polar pi bonds. That is still a Michael acceptor. We do have that attack in there because we can still get resonance across out just like we could with a carbonyl. The nitro group tends to be a favorite one to be tested on because when we look at that, where's the carbonyl? Right? There isn't even a carbon to nitrogen polar pi bond. What is it? It's a nitrogen to oxygen pi bond. And because we're extra obnoxious with this functional group, we almost never write out the Lewis structure, probably because there's so much charge in it and we don't like looking at it, so we hide it all. Okay? Students tend to not see the nitro as that functionality. The carbonyl polar pi bond is still there. We still get that 1,4, that alpha beta unsaturation of the pi bond. Kind of, sort of? Okay? Those are all acceptors. They're all acceptors because what are they doing? Accepting electrons. So really this is just a fancy way of saying electrophiles. To be Michael, they have to have that alpha beta unsaturation. Otherwise, they aren't Michael acceptors. Okay? What about the donors? Well, what are they donating? Electrons, which makes them nucleophiles. When we go through and look at each of these nucleophiles, what do each of these have in common? Lots of resonance. They're between two. We don't see single enolates. Why do we not see single enolates? Single enolates will do 1, 2. Michael is specifically about 1, 4. We need 2 resonance structures to stabilize that carbon nucleophile for them to be an official Michael donor. So when we go through and look at all of these pieces, you'll notice that they do get a lot of resonance stabilization. You see the nitrile coming in again, okay? Again as kind of a tricky thing. But remember, polar pi bond. It fits the category for our carbonyls, polar pi bonds. You'll notice the Gilman shows up in there. Well, that doesn't match polar pi bonds. The Gilman's kind of that weird one. The Gilman does 1, 4 additions. Okay? Last one, what's going on with that? We still see the nitro, but I only see 1. Why only 1? Didn't I need 2?
Same thing like that.
Well, it's the same thing over here. So yes, it withdraws. And by withdrawing, it can make that negative. But in this case, it withdraws and withdraws. Withdraws and withdraws. Withdraws and withdraws. What's this one? Withdraws. Why is this one okay as just 1 withdrawal and not 2? It has to do with the electronegativity of that nitrogen. That nitrogen is so electronegative that it's withdrawing those electrons with the force of 2 resonance effects with oxygen. Okay? Extra little bit of tidbit, it's not even just its electronegativity. What happens if it withdrew electrons? What happens to the positive charge on the nitrogen? It would exceed the octet, so I break the pi bond. What would I draw? So there's R. Yes, I would draw resonance. Yes. Two negative charges. What happened to the nitrogen? It stays positive. Even as a withdrawing group to withdraw electron density out, even when it accepts more electrons, it still wants more. Okay? That's why nitro is such a good withdrawing group. That's why it works great for a Michael donor. Okay? Enamines, conjugate addition reactions. Okay, remember we had the enamine? Okay. The enamine could also be used as 1,2 or 1,4. What do you think? Okay. Consider it. Think about it for Wednesday. They also have an extra added benefit when we're looking at our enamines. If we were to go through and draw the enolate for our carbonyl and we drew on a methyl group, right, when I react that with a base, where does my enolate form? Left or right? Right, let's use just a standard ethoxide base. Ethoxide, where do I deprotonate the enolate? Ethoxide is a strong base, not stupidly strong, so the enolate is the thermodynamic enolate. When we form the enamine, if I did the exact same reaction with ethoxide, where does it deprotonate? Deprotonates on the kinetic side. Right? We will come back and look at that one a little bit closer, but those of you in lab should know that answer because that is exactly why we use the enamine in the WMK mechanism. One of the post-lab questions. Don't worry, everybody got it wrong. Okay. Our conjugate addition reactions, there's a giveaway for our answer. Last thing, Robinson annulation is now stacking a Michael addition on top of an aldol condensation. Okay. Why can we do this? Why is it important? That structure is a precursor to anti-cancer drugs. Okay. Because it was so important of a discovery, guess what happened? They got to name it, even though it's a combination of already named reactions. Right? Yeah. Just run a bunch of named reactions together and you get to attach your name to it. It's kind of how it works. We'll look at a mechanism on that. Oh my gosh, there's a lot more slides than I thought. Okay, but we have to end anyway.